lesson 8.2, apply exponent properties involving quotients. You should be on page 495. Now remember, the word quotients means division. So we're looking at applying exponent properties when we have division problems. Notice what happens when you divide powers with the same base. For example, a to the fifth would mean 5 factors of a, which you can see here as I'm circling them. A to the third would mean 3 factors of a, which I'm circling those. And you notice if I can cancel out 3 factors of a in the numerator with 3 factors of a in the denominator, and what's left is a squared. So a to the fifth divided by a to the third is a squared, which suggests the following property. It's called the quotient of powers property. You already probably figured out what is the shortcut to this, and here it is in words. To divide powers having the same base, you subtract the exponents. And you can see that here. 5 minus 3 would have given me second power, a to the second power. So here would be an example of that again, 4 to the 7th power divided by 4 to the 2nd power. Since the base is the same, you should be able to quickly subtract the exponents, and you would have 4 to the 5th power. I'm going to have you pause the video for a minute. Go ahead and try these. Okay, we're back. You notice we have the same bases here. This would end up being 6 to the 6th power, because 11 minus 5 is 6. Here we have the same base. This would be negative 4 to the 7th power. Now here, in number 3, this is a multiplication property to start. I have the same base, and when I multiply, I add the exponents. So this is really 9 to the 7th power in the numerator, and I have 9 to the 2nd power in the denominator, and now I can subtract. I would end up with 9 to the 5th power. These always cause problems, okay? Because of the 1 in the numerator, people aren't sure how to handle them. Go ahead and put a 1 in the denominator, and now you're multiplying fractions. When you multiply fractions, you just multiply across. 1 times y to the 8th is y to the 8th. And y to the 5th times 1 is y to the 5th. Well, now that should be easy. I can subtract the exponents because I have the same base and I'm dividing. That would be y to the 3rd power. The second property you're going to learn today, and there's only 2 properties with division, it's called power of a quotient. Notice what happens when you raise a quotient to a power. So here we have a over b in a fraction to the 4th power. And you can notice if we are going to take a over b, and we'll write it out 4 separate times because there's 4 factors, and I circled that here. I wrote a over b as 4 separate factors. Well, can you see how I have 4 factors of a in the numerator and 4 factors of b in the denominator? That's simply a to the 4th over b to the 4th. The above example suggests the following property of exponents known as the power of a quotient property. To find the power of a quotient, find the power of the numerator and the power of the denominator and divide. So in other words, this is saying you have to apply the exponent to the numerator and the denominator, and then you can try to divide at the end if they have the same base. Like here would be an example. Here I have 3 halves to the 7th power. I must apply the 7th power to the numerator and the denominator. That's why I have 3 to the 7th over 2 to the 7th. These do not have the same base, so I am not allowed to subtract the exponents because the bases aren't the same. Same thing here. Why don't you try these and pause the video, and then we'll do them together. Okay, we're back. This first example should be a to the 2nd over b to the 2nd. This next example, we have to cube the negative, so that would be, keep it negative, because if we have 3 negatives, that's still negative. 5 cubed is 125, and then I'd have y cubed in the denominator. I had to cube all three items in there. Here, I got to take x squared and square it. That would be x to the fourth. Remember, power to power we multiply, but now down here in the denominator, I got to take 4 and square it. That would be 16, but I also have to take y and square it, which is y squared. There's the answer to that. And then for this problem, I got to take 2s over 3t and cube it. I got to cube 2, which is 8. I got to cube the s. In the denominator, I got to cube the 3, which is 27, and I got to cube the t. But now I have to multiply by t to the 5th over 16. So before I start working all this out, I can do some easy canceling. 8 goes into itself once. 8 goes into 16 twice. And t, you notice here, I'm dividing with the same base. I can subtract the exponents. 3 factors of t down here will cancel with 3 up here and leave this second power. I'm going to end up with 1s cubed t squared all over 27 times 2 is 54. And there I simplified that. Okay? They'll have you solve some word problems. There's an example here. I'm going to skip over that. You can read this one on your own. And let's look at this one because this involves order of magnitude. I always like reviewing that. Solve a real-world problem. And you can see here the luminosity in watts of a star is the total amount of energy emitted from the star per unit of time. The order of magnitude of the luminosity of the sun is 10 to the 26 watts. Remember, order of magnitude is rounding to the nearest base 10. The star Canopus is one of the brightest stars in the sky. The order of magnitude of the luminosity of Canopus is 10 to the 30th watts. And they ask, how many more times more luminous is Canopus than the sun? Now, sometimes it's easier, again, to use simpler numbers. I want to know how many times more luminous is Canopus than the sun. So let's just pretend, I'm just making up numbers. Let's pretend that Canopus was just 10 watts. Let's just pretend that this was 10 watts, and let's say the sun was 2 watts of luminosity. And I want to know how many times greater is Canopus than the sun. Well, that would be easy. 10 is 5 times greater than 2 because I would just be doing 10 divided by 2 and getting 5. So the answer to the problem is a division. I should be taking 10 to the 30th divided by 10 to the 26th. Well, that should be easy, and you can see they're doing that right here in the book where I'm circling. Since I have the same base, I can subtract my exponents, 30 minus 26, 10 to the 4th power, which would be about 10,000 times greater. So the star Canopus has a luminosity that is 10,000 times greater than the sun, according to this quick calculation. I'm going to pause the video there. If you have questions, make sure you ask in class.